let's see here. We are a little bit behind, but I think we should be fine here. Make sure we just get everything set up. Okay. All right. I think with that, we should be good to go. Let me just make sure we have all that we need. Okay. I think that will about do it for that. Let's quickly get this last bit here set up, and we should be good. Okay. All right. This is going to be our 8th live stream together for another AP Calculus free response packet that we can go over together. So this is going to be the 2012. We need to make sure we have that listed properly on the screen here. The 2012 AP Calculus free response question section. And we will be able to have the entirety of all 6 problems of this packet answered. So just like we have done numerous times before, we have ourselves the AP Calculus 2012 free response section and all of the questions that we will go over individually, going from 1 through 6. The first 2 of which are done through with a calculator, and then the last 4 not having a calculator through it. Okay, and so with that, we should have all that we need to move forward with this. Let's make sure we get everything complete here. All right, so as we've done a number of times before, all of the questions will be written down first on this notebook here, so that the problems can be easily walked through along each section, and we grade ourselves out of all of the available points that this test allows for. And so with that, why is this no, I think this is the way that shows. Okay, yep. So because of that, we can have all the things that we need to go through this. The first 2 problems will be done whenever there's anything needed on a calculator, my trusty TI-83 Plus graphing calculator. And so we should have everything we need. Again, all of the questions that anyone would have can easily go through the either the main live chat or our email at the labcodemath@gmail.com over onto the left side. Okay, so without any further ado, why don't we go ahead and get started on the first problem. So again, I'll be copying down all the main problem points, including the table that's involved, and we should be going through each individual problem together, and any other questions will be followed up on as well. Okay, so let's see how this goes as we move through this. Okay, so question number 1. We have ourselves first a table, so this is the time in minutes, and the W of t, which is going to be in degrees Fahrenheit. So we have multiple points: 0, 4, 9, 15, and 20. Okay, if the camera decides to focus a little bit on this, it's a very odd way of deciding what to focus on, especially with all the light shown on there. Hello, would you mind, camera? Okay, good. All right, so we have all of those points, so let's put in the function for W down at the bottom at 55.0, 57.1, 61.8, 67.9, and 71.0. Okay, it says here that the temperature of water in a tub at time of t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. Okay, and also it gives a point here that at time is equal to 0, the water is at 55 degrees Fahrenheit. Okay, and then it also says the water is heated for 30 minutes. Okay, beginning at the time is equal to 0. Okay, and then we have the rest of the table to look at from there. Okay, so I want to double check here if we can have it like that. Okay. All right. So it says here for problem A, this is all the context that we have for the problem. It says here to use the data on the table to estimate the W prime of 12. Okay, and it then asks us to show the computations that lead to your answer. Okay. And then it says here it's using correct units, interpret the meaning of your answer, in the context of the problem. Okay. So a little bit of an interpretation of what that's going to be. So W prime of 12 is what they're asking for to begin with. Well, that means that we're going to have to do, if it's an estimation of a derivative, that means we're going to use the average rate of change. And now we must determine then, as the students trying to solve this problem, as to what would be the best candidate to use for the W prime of 12. Of course, we need points that are going to be outside of W prime of 12, so that what would be right in the middle would be the actual average itself that we're looking for. So the average between 9 and 15, well, that's going to be, I think that will be the best choice, because 12 is right in between, being 3 away from 9 and 3 away from 15. So choosing 12 on that matter seems to be the best option for that. So we can very easily set up the average rate of change equation for ourselves, which is going to be the W of 15 minus W of 9, so the Y values for each of them, all divided by 15 minus 9, the change in the X values for that. And so we have everything we need to start plugging that in. So 67.9 minus 61.8, those are values that are directly from the table for the W of 15 and W of 9. So by dividing that by the difference of that of 6, we can then run this calculation. Thankfully, because this is a calculator section, we can quickly run that through without much of a problem with the 67.9. If it will decide to show properly the actual calculator without I wonder what will be best for that. It always seems to be a little bit of a struggle to make sure we can even see the calculator every time we use this. But if I just hold it up like this, I think that should be able to work for now. Even though there's light coming from all the sides of my room. So 67.9. Well, let's make sure we put that first. So subtracted by 61.8 and divided by a whole 6 there. So we get 1.017 if we round it properly. So 1.017. And in terms of the units that we need to show here, well, we divided by the degrees Fahrenheit on the numerator, as those were the values that were on top, and we're dividing it by the minutes in the bottom. So that's degrees Fahrenheit per minute. Okay, again, so which will then mean is the rate at which the water in the tub is being heated. Okay, so at least for that, that is going to be, should be an acceptable answer for us to show what the approximation for that derivative will be like for that problem. Okay, going on to problem B, it says here to use the data on the table to evaluate. Oh yes, that's right. Let me change that right now. Okay, so to evaluate the integral from 0 to 20 of w prime of t dt. Okay, and we also need to show units as well. All right, so for us to begin with, the integral from 0 to 20 of w prime of t dt, well, we have to use good old fundamental theorem of calculus, abbreviated as FTC, for ourselves. And with that, we should be able to then understand that by taking the integral of a derivative of a function using fundamental theorem. That is just going to be w of 20 minus the w of 0 as a result of that. Okay? And we're going to go back to the original function, so we can easily put back in those points of 71.0 minus the 55.0 as shown exactly on the table, which will then give us a whole 16.0 as a result. Okay, so going back to the original function of w as a difference of the two of that, that is just going to be the degrees in Fahrenheit. Okay, but in our case though, what that means for us is that we took that difference between the 2 points in those times of 20 and 0 minutes for that function. So that means that that is the change in temperature of the water in the tub from 0 to 20 minutes. Right? And that's what that definite integral is showing us. We're just taking the difference between the two limits of the integral of the derivative of w of t. So with that, we're just looking for that change that was there from the 20-minute mark down to the 20-minute mark at 71 degrees Fahrenheit to the 0-minute mark at 55 degrees Fahrenheit. Okay. Then going forth, it says here that for the interval from 0 to t to 20, it says here to find, not find, it says the average temperature of the water in the tub is known as 1 over 20, the integral from 0 to 20 w of t dt. Okay. Then it says here to use a left Riemann sum with the 4 subintervals by the data in the table to approximate that 1 over 20, 0 to 20 w of t dt. Okay. And then they're also asking that if it does this approximation, overestimate or underestimate the average temperature of water over the 20 minutes. Okay, so we got a few things going on here. Is that we need to use that left Riemann sum showing right there. So we need to use a left Riemann sum with 4 sub-intervals there, and we need to then show if we're going to do an overestimate or underestimate of what we have on the graph. Okay, so because of that, well, if we want to estimate that integral going from 0 to 20 w of t dt, and that approximation will then mean that we will then need to go ahead and see what we need in terms of this Riemann sum with 4 subintervals. Going back to the table that we have here, we have already 5 points here, which is exactly perfect for 4 subintervals, keeping the fact that we are using the left-hand points as the left Riemann sum for the left heights of the rectangles that we're going to draw. So we have 1, 2, 3, and 4. 55, 57.1, 61.8, and 67.9. Those will be the valid heights for this type of sum here. And so with that, we can go ahead and see what that looks like in terms of the actual average temperature by keeping that 1 over 20 as a coefficient on the outside to show that we're doing the average value of the function after we estimate what that Riemann sum will look like. Okay, so with the 4 subintervals, we will then need to put in each one of those heights, so 55.0, and then we need the base of each rectangle. So going across is from 0 to 4, gives us a base of 4 on that rectangle. Adding that with then the next base of going 4 to 9, that's a base of 5. And going across, that's a base of 5 for that rectangle that's coming across that side. So it's 5 times, and the left-hand height is a 57.1. And then going from 9 to 15 will be a positive 6 base. So it's 6 multiplied by the 61.8. And then lastly, adding in from 15 to 20, that base is going to be a 5 with 67.9. 5 multiplied by 67.9 on that side as well. Okay, so along with that, we have ourselves a few things to go over right here in terms of the actual calculation itself. So let's run that really quickly through our calculator here, which if I just do it, okay, interesting how it catches that shadow just so perfectly on the screen of the calculator. That doesn't help my case if it does that. Okay, whatever. We're just gonna have to deal with the fact that it's gotta angle it upwards to catch all that light onto the screen. Very good. So let's go ahead and do 55 times 4 as the first rectangle, and then adding that with the 5 times the 57.1 as the next rectangle, adding that with a 6 times 61.8 as that rectangle, and lastly adding it with the 5 times 67.9. Okay, so by running all of that, we get the final Riemann sum of 1215.8. Okay, so that is just the approximation of that integral from going from 0 to 20 on w of t dt. But that's not all that they were asking for. They wanted to know what that average value is by dividing all of this by 20 after the fact. So 1215.8 divided by the 20 right there. That will give us the average value for ourselves. So by dividing the answer by 20, we get 60.79. And now we'll be back to degrees Fahrenheit, as this is the average value of now the integral of the actual function itself, sorry. So wt from 0 to 20 minutes. Okay. This is supposed to be for a moment for the students to realize what they're dealing with in terms of the actual problem itself. Okay, but that also means that we still are asking if it's an over or underestimate for the actual Riemann sum that was just found. So what we notice here is that we have an increasing function, as that's what they were telling us the whole time, right? As these values across the table are going higher from 55, 57, 61, 67, and 71. So all those values are increasing. So the function that is going higher upwards, if we keep choosing the left-hand points to make our sums across, right, with our rectangles, you'll notice that we are going underneath the function, right? So increasing function with a left Riemann sum. Of course, what that would mean instead is that because we keep choosing the left-hand points while the function keeps increasing with the Riemann sum, this will then end up with an underestimation of that integral from 0 to 20 w of t dt. Okay, so that will answer the second part of the question for us as to what kind of an estimation we are dealing with from here. Okay, so let's get lastly to part D over here. It says here that for the interval from 20 to t to 25, the function w that models the water temperature has the first derivative given by the w prime of t being equal to 0.4 square root of t times the cosine of 0.06 times t. Okay, so based on that model, what is the temperature of the water at the time is equal to 25? Okay, so here we've got ourselves a few things going on here. Is that we have the actual first derivative w prime of t given by this type of function, okay, where we go from 20 to 25 minutes, so beyond what the table has already provided us. But then we want to know the exact temperature of the water at 25 minutes, okay. So we then will need, off of that, a little place to understand what is happening here, right? Because all we have right now is w prime of t, right? So we have that, but then they want that, what they're asking for is the actual original function w of 25. That is what the question is asking for. Okay, so given that this function w prime of t only works from going to 20 to 25 on the t, that means that we're going to need at least one other point for ourselves in order to use fundamental theorem of calculus, right? If we want to go backwards from w prime of t backwards into the original function, right, we would need an integral. But thanks to fundamental theorem of calculus, we do know that if we then have actual limits to this type of integration of w prime of t dt, that will just mean we have w of a minus w of b as the sorry, it's wb minus a. W of b minus w of a of the original function is what we're looking for, and we just need one more point because we can run this calculation. That's going to be done on the calculator. Well, the w of b minus w of a, right? Again, one of these we can have known as the w of 25. We just need something else to be known for the w of a for the original function of w, which thankfully, given that we have the limit of 20 as one of them, we already have ourselves one of the data points for w of 20 as shown on the table of the beginning of the problem. So we can set up our equation as such as that if we have a definite integral from going from 20 to 25 of w prime of t, we can then have it so that we are reverting back to w of 25 minus w of 20 as given on the fundamental theorem of calculus. But by adding the w of 20 to both sides of that equation, we can then isolate w of 25 being equal to w of 20, which is a data point. Again, this data point was already given to us at the start of the problem as 71. So with that being already established, it will be 71 plus the integral going from 20 to 25 of that w prime of t function, which we can just copy straight from the problem of 0.4 multiplied by the square root of t times the cosine of 0.06t dt. Okay, so with that, we have everything we need. This guy can go straight into the calculator for ourselves after we completely set everything up for the fundamental theorem of calculus. So with that, we can then acknowledge ourselves that we have 71 on the outside, plus then I can run the function integral operation on my calculator. So we can then plug in the actual function itself, w prime of t. So starting with 0.4 multiplied by the square root of, we can use the variable of t on this, square root of t multiplied by the cosine of 0.06 times t again. Okay, so with that function in there, we can then call it that the variable of t is going to be integrated now going from the limits of 20 to 25. Okay. So with that line of work done, we can then figure out that the actual function itself will take us to 73.043. Okay, so 73.043. That's going to be in degrees Fahrenheit, and that answer does match, at least for the most part, because it did state in the beginning of the problem that it is strictly increasing. The entire temperature of that water inside of that tub is going to be increasing the entire time, going all the way up to that 25 mark, which at a 73 degrees Fahrenheit status at the end of our time does make sense as an increase from where we had there earlier. Okay, so that does match. And so we did answer that question of what is the temperature W at 25 minutes. Okay, so that should do it for problem number 1. Again, for those that might be here for the first time, we go through 2 problems at a time, so 3 sets of 2, before we go and check each individual problem to see how many points we would have received from the answers that we have. So we'll go over to problem number 2, which is going to be the other problem for the calculator section of this exam, and we'll see how we can respond to those. So we have a little bit of a graph going on here, as you can see, so this will all be copied down and we'll be answering parts A through C here. So let's have ourselves a look here. So problem number 2, which is shown right there. Okay, so problem number 2, we have ourselves this region right there. So 1, 2, 3, 4, 5, going across 5. I think we should go like 1, 2 there, 1, 2 right there. So go 1, 2, 3, 4, and 5 like that. Okay, starting at 1, 0, we'll go up to some point up there. So it's underneath 2, after a little bit after 1, end at there. So we have something like this there. And we have the region of R described as such. So the problem itself is going to tell us that let R be the region in the first quadrant bounded by the x-axis and the graphs of y is equal to the natural log of x and y is equal to 5 minus x as shown. Okay, so we have those two functions there, y is equal to the ln of x and then 5, well, that's not really good. Let's rewrite that. So that's y is equal to 5 minus x. That is a better showing of that function. Okay. So with that, that's all the context they're going to give us. So first they said we want to find the area of R. So then we need to go ahead and find that area between those two functions. Thankfully, we can easily see that we have bounds between x is equal to 1 and x is equal to 5, as shown on the graph there. Okay, and so because of that, we need to go ahead and make sure that we show that we are going to do the actual part here where we are integrating between the that function, which is the natural log of x, being that it's 1 comma 0. That does make sense for the natural log of x. We go up there up to that certain, now that's not a whole number, that's going to be at the intersection. So we need to find the intersection of the natural log of x and 5 minus x, so that we can then transition between the two integrals. Right, so we're going to have two separate integrals, one of which is going to go from 1 to, let's call it c for the intersection on the definite integral. Right, and that will be the first function, which is the natural log of x. And then we need to take it from that intersection going all the way to 5, where the interval ends for this guy. And then we take it for 5 minus x dx, as we are transitioning between two different types of functions to know the difference in the heights between the actual axis and the function right there. Okay, so in order to find that intersection, of course, we can then just graph the actual two functions itself. So y is equal to the natural log of x, and the y is equal to 5 minus x on our calculator, as this quiz question number 2, which is still a calculator section. And we can go ahead and see what this looks like graph-wise, and then we can calculate a nice and easy intersection. So showing here, we have we can put in the two different guys. So the natural log of x being the function number 1, and then we can go for 5 minus x, which is going to be function number 2. Okay, so with that, I think we can set the window from going up to maybe 6 on the x. That does make more sense there for us. And then maybe the y min should be -1. We're going to stay all on the positive side there. So with that, as you can see, we have ourselves that natural log of x curve showing up, and then we have that linear line right there. So that intersection, let's go ahead and see what the coordinates of that is going to look like. So we can go ahead and trace an intersection, option number 5 on this calculator. And from there, our first curve will be somewhere close to the intersection. So let's just call it, I think, right there. Our second curve will be close there as well. So it's going to go and run a few iterations for us to get the intersection of x being 3.693, it looks like. Okay, so intersection. So x is equal to 3.693. And then the y is equal to 1.307, if that is rounded properly on the y side. Okay, so because of that, we then have our c. That's our limit for the two integrals, so that we know where to switch off between going from the natural log of x and then continuing back down on the 5 minus x graph. Okay, so in that case, the area will then be equal to, from going from 1 to 3.693, with a natural log of x dx, plus going from the 3.693 all the way to 5 of 5 minus x dx. Okay, so these two can very easily be put into the calculator, and so with that, we can go and see with our own ability here with the function integral operation that we are integrating for the natural log of x, that's y, of x, for the variable of x going from 0, not 0, sorry, to 1 to 5. Did I write down zeros? No, I did write down 1, that's what it should be. Going from 1 to 5 on that first integral, then we're adding it as not 1 to 5, what are we doing? 1 to 3.693. Okay, so that's where that point was on the intersection. And then we need to add it with the second half of it, which is going to be the integral of this now, of the 5 minus x function for the variable of x going from that 3.693 all the way to 5 as the ending right there. Okay, so those two can be added in together, and we get a total area of 2.986 if we round that properly. 2.986 is going to be the area between those two functions, as we know how to transition between one function to the next as we are measuring all those collected heights from the x-axis up to the end of the function right there. Okay, so it says here then at part B that region R is the base of a solid. Well, I like where this is going already. This sounds like a great volume problem already. So it says here, so for the solid, each cross-section is perpendicular to the x-axis is a square. Okay, then it says here to write, but do not evaluate an expression involving one or more integrals that give the volume of the solid. They give the volume of the solid. All right, very nice. So we have ourselves a few things that go on here in terms of the actual happenings of this type of problem here. So we have the perpendicular cross sections of squares going across. So again, is perpendicular to x-axis, so that's going to be an important note right there for us. But also we are looking at squares for the actual areas that we are all adding up for this type of guy here. Okay, so given that it's a square, and that means the volume is just going to be, in the generic sense, the function multiplied by itself inside of the integral. The main issue, of course, just like how we did for the area, is that it is not just as simple as just doing one function. We need to split it between two guys where the intersection at 3.693 is going to occur as we hand it off between one to the next function. Okay, so because of that, the volume then is going to be, instead of just one nice integral, we will start at 1 going in terms of the integrals. We start at 1 and ending at 3.693. In this case will be the natural log of x function. Okay, but this guy is going to be squared, as that is the base of the square that is going to be measured, and multiplied by itself, of course, will give you the area of the square that we needed. And then we need to add that with the second part, which is the 3.693 all the way to the positive 5. This time of the 5 minus x, all of that squared dx. So again, instead we're going to square each individual part by themselves, and adding that all the way up will give us that total volume of that solid that they are looking for. Okay, so it really is just a simple matter about what is being asked, as well as the actual total understanding from the students of what is really being talked about in terms of finding a volume with cross sections of squares that are perpendicular to the x-axis. Okay, next up here it says that the horizontal line y is equal to k divides R into two regions of equal area. Okay, and then it tells us that we need to write but do not solve an equation involving one or more integrals whose solution gives the value of k. All right, so we have ourselves quite an interesting prospect here, because let me just double check on the volume of this right now very quickly here. Okay, but we have ourselves a very interesting prospect on this, because we need to find some sort of k in which this guy here, so I think I should switch color here for just a second. Let me get my nice and bright blue here. So there will be some value of k. We don't know exactly where that is, but there will be that line of k. Maybe a whole line will be easier to see, right? So that line of k, that's going to split this area directly in half. Okay. The main issue, of course, is that we don't know if it's going to be before or after. For the most part, it definitely should be after, because that's actually kind of the highest point for either of them. So that wouldn't make any sense to be past that point, because we wouldn't really get anything beyond that. Okay. So with that in mind, we then need to see to it that by going from that y is equal to k line, okay, we need to see to it that we show the integrals in which that is going to be the case for us. All right. So we already know then that because we are going horizontally now, I wonder if we can try to do integrations horizontally as well. That might not work as well as well. I mean, I think that actually might work as well as we need it to. Yeah, why don't we try doing that actually? So, in terms of what we're doing here, okay, if we then instead, so with that same region, right? So a quick sketch of what we're dealing with right now is that instead of integrating in the vertical sense of finding the areas, what if we swapped it into an integration in the horizontal sense instead, right? Because of that, we can know where to stop because we're integrating on the y is equal to k, so whichever part that line of k is going to be. We can stop the integration exactly at k as a limit if we're going vertically instead of horizontally on the integration. And if we did it in terms of dy, because you know that y is equal to k is going to be a limit that we can solve for once we run a few problems. Okay? So, why don't we try doing it this way then? Right, so instead of calling it y is equal to the natural log of x and the y is equal to x minus, or 5 minus x, sorry, 5 minus x as the two functions, we can swap it around where e raised to the y power is equal to x and the x is equal to 5 minus y instead. Okay, so by swapping things around in terms of x instead, we can then run this as a horizontal integration in terms of y, because y is now going to be each of those functions that will be integrated for, and this should be done actually in one motion on one side of the problem instead of splitting it up into multiple. What I mean by that, of course, is that if we go, of course, because we do know that y value of that intersection as well. Again, the intersection, if we needed a refresher there, intersection for that point is going to be 3.693 on the x value, but it was 1.307 on the y value that we did record earlier in the problem. Meaning that this is going to be the end of the integral, because that was the highest point at which those two ever crossed. And so, because of that, we can actually run this integral now. Because we're going in on terms of the y values, the y starts at 0 and needs to stop at k, because that's where the halfway point is going to be for this integration. So by going from 0 all the way to k, we just now need to do the horizontal integration of the larger function, again measuring it horizontally away from the y-axis of this, again the 5 minus y, that's the larger function, while the e to the y is going to be the smaller function. So we just need to run a simple subtraction here, so 5 minus y minus e raised to the y power dy. That will be the way to integrate for the first part, but then that also means for the second part, we then need to go from k to finish it all the way to the end of the 1.307 of the same issue though. It's 5 minus y subtracted by e to the y dy. So that way, we have the actual values of k waiting for us in that equation. If we really wanted to show everything on one side to make equal to 0, given that we can go and start putting all that together. So minus k to the 1.307, 5 minus y minus e to the y dy. Again, that will show that those two are going to be equal to each other, and if we were to graph that on the graphing calculator as such, that will show up as something that we can then figure out easily for the value of k. Okay. I think also because we already gave the, I wonder if also this will consider as an answer too, because we already gave the answer of the entire area. So we already know that the area is equal to the 2.986 as from problem 1. So just by dividing at 2, we get 1.493 as the area of 1/2 of that whole part of the integral that we need. So I think if we also want to do it this way, we can just set it as 0 to k 5 minus y minus e to the y dy subtracted by the 1.493 will then be equal to 0, because again this was already 1/2 of the, that was already 1/2 of the area to begin with from our earlier part. Okay, so that way we can leave it as one integral, as we can simply solve for k now as the only unknown for this type of problem. Okay, I think that should about do it for the first two questions on this exam. So we can get over to that really quickly and see how we scored. So just as a recap for anyone else who might be here for the first time watching this on the VOD, is that we do have the old scoring guides, which has all the answers to the problems, as well as each way that they are looking to grade this. Okay, so I'll be looking through this and marking up my notebook as such to make sure that we are on the same page about this type of equation. All right, so to begin with here, it says here that for part A is that finding the part one, question number 1, that is. Okay, so question number part A, yep, by doing the average rate of change that we've shown here, right, our estimation does show that it should be 1.107 the degrees Fahrenheit per minute. Again, that is going to be the rate at which the water is being heated. That's exactly the right interpretation for those units, with the Fahrenheit up on the top of the fraction, minutes down at the bottom. So by that, we get 2 out of 2 correct for that problem. Then going to part B, we run the actual Riemann sum. Oh no, that's part C, sorry. It's going to be the actual fundamental theorem of calculus to show that yes, we're subtracting w of 20 minus w of 0. So we do get the value of 16 degrees Fahrenheit over the 20-minute period, with the change of the temperature between the 20-minute mark and the 0-minute mark of that water inside of the tub. So both of those are exactly what they're looking for. That is going to be 2 out of 2 correct for this part. Okay, then going to part C here, we have ourselves that by using the left Riemann sum for this type of integration here, we can then run the actual summation of it. So again, each individual base multiplied by the left hand heights was exactly what they needed, and we do get the actual approximation of 60.79. Right, so the formula setup was correct of just doing simple rectangular areas across the 4 different heights that they were looking for, resulting in 60.79. But then we then realized that it is an underestimation, of course, because the increasing function does the exact reasoning, right? An increasing function taking the left-hand points and moving across it as the total height of a rectangle means that there will be plenty of gaps underneath the actual function itself, and so leaving it as an underestimation will give us 3 out of 3 correct for this part as well. Okay. Then lastly, going to part D, we have the water at 25, okay, the 25-minute mark temperature, and then we need to use fundamental theorem once more for us to realize that if we add 71, which is the w of 20, the one part that we do know, and run a definite integral from 20 to 25 by plugging that straight away into the calculator on that integral is what they're looking for, then we do get a result of 73.043. Okay, so that's 2 out of 2 correct on part D as well. Exactly what they needed, as for us to show that we understand exactly how to use the fundamental theorem of calculus to find those results. Alright, so because of that, that is going to be a total 9 out of 9 correct for problem number 1. what I like to do is to make it easier for us to grade our totals at the end of every session, is that at the front of the page, we can write down each of the problems. So question 1, 2, 3, 4, 5, and 6. And with that, we can write down out of how many problems we got. So 9 out of 9 on question number 1. Then we can add everything up and get a total out of 54 for the total amount of points that we received on this packet. All right. So going to question number 2 here. And move down a little bit more. Okay. So yes, we're looking for that region that we needed to find the area of to begin with. And what is that? Oh yes, because that is well, they did the intersection. Okay. Yep, the intersection was exactly correct. 3.693. That's fine. But problem number A though, finding the area of going between. Oh, they switched to dy as possible reasoning, but we did the second answer here, which was going to be finding out the intersection of doing ln of x dx, adding it with the next part of 5 minus x. So that's completely fine of them showing that 2.986 is going to be correct. The limits of integration is what they wanted to show, as well as the setup for the problem itself to know that we are splitting this into 2 integrals so that we can find the accurate area of region R. So all that is good. That is going to be 3 out of 3 correct for us on part A. Okay. Then going to part B here. All right. So the volume itself means that yes, we will have to then run. You have to run it now in terms of dx because they did tell you that it's perpendicular to the x-axis, meaning that we need to measure it by height going all the way down across that region. So showing it as the correct spot where the intersection is going to happen if you split it between the square of ln of x, because again we're finding areas of squares that we are integrating across those limits, as well as the 5 minus x, all that squared. Both of those are going to be the way that they want to show the volume part. And expression for the total volume, putting it all together, is going to be the third point which they're looking for, giving us 3 out of 3 correct, as just this was a problem that just asked for the setup of the integration, not the actual volume itself. Okay. Then going on to part C here, it's going to be another setup here for the volumes. Now we can put this either as putting as 1/2 times the 2.986, so running the actual 1/2 mark was going to be acceptable, as by swapping it in terms of dy, that was the simplest way of showing how to find that value of k, by swapping the variable to a dy sense, because as shown, if we can then just run it horizontally as the areas that as we calculate going up this up the y-axis, that means we can stop at the limit of k as part of the integral, and we can leave that as such to be shown there. Okay, so because of that, that setup is exactly going to be correct for the integration. The limits going from 0 to k was exactly what they were looking for, to make sure that they understand where to stop the integral. And then the total equation itself, again, I can move it over to the right side, should be fine, as it's a way to put that into a graphing calculator if this was in any means to show this as such. So with that, that is 3 out of 3 correct there. Our boy Nicholas shows up in the chat, of course, saying that we are indeed back for more Math Madness, no doubt. It is Thursday, so we got to get through another packet together to make sure all of our math subject is right on track. So that will finish up question number 2 for this part of the exam, which now, as a record for what we're doing so far on the first third of this exam, I'd say we are quite good, because that is all 9 points on question number 2 complete as well. So maybe, just maybe, this will be the day that we can get a 54 out of 54 on this packet in the history of this channel. This is not yet to have happened yet, so who knows what is possible. We can definitely go and try to see what our best score is going to be like. Okay, so with that, we have everything we need to move on to question number 3, which now is going to be no calculator section, so I'm going to put my trusty TI-83 away. It's no longer needed for the rest of this exam, as we get on to problem number 3. Okay, so I'll be copying over this graph again as this is something that we'll be referring back to, and all the problems as we go through this section together. Okay. So, yes, our long time, almost, I believe Mi Jin Yang would be one of our first subscribers. She is cheering us on. Yes. Thank you very much. It is definitely needed for us to continue successfully to get through the rest of this exam packet. All right. So, let's go to question number 3 here. All right. So, let me go ahead and quickly move over this entire graph that we have here. I think this should be fine. We only need to go a height of 3. Okay, so we go 1, 2, 3 up there, and then we need to go across 4, 1, 2, 3, and 4, and then across under the 3 on the right side. Okay, so what we have here is that we have the point -4, 1, -2, 3 up there. Okay. Oh yes, yes, Claire. We do have graphs coming up here. That is going to be a very big disappointment for many people, but it is definitely needed for us to show to the AP test people that we know exactly what we're doing. I know some people have certain t-shirts saying that they have no idea what they're doing, but in any case though, we at least need to have some semblance of being able to solve these types of problems. So I'm just simply copying over what they're putting on this graph here. We have a semicircle, looks like, between there, and we have that. Okay, it takes a note here that this is the graph of f. Okay, very good. So with that, the context of the problem says that we have f is continuous, defined on -4 to +3, whose graph consisting of 3 line segments, 3 line segments, and a semicircle centered at the origin, is given above. Okay, and they also say here that we will have another function, so let g be given by g of x is equal to the integral going from 1 to x of f of t dt. All right, so we have ourselves quite a few things going on here for this type of graph here. Also, I think this is a perfect time to shell out that for all of my friends, all they're waiting in the chat, why don't you slap that like button, because I only have 2 right now. That'll be a great time to slap it to move it a little bit up that needle. But nonetheless though, let's get on to part A right now. That they want us to find the values of g of 2 and g of -2. Okay. If you get rid of the graph, he will hit the like button. Yes. All right, Nicholas. That is unfortunate that I cannot do that. We still need to finish this problem first. Maybe in another 10 minutes. Then it will go through. Oh yes, Claire wants me to do a TikTok dance. Wow, my own viewers are holding me hostage on likes. What a great community that we are building up right now. My goodness, I'm actually here doing a great service for students, and now I'm being held hostage to do a bunch of random nonsense for my own viewers to hit the like button when they tune into the stream. What a great world we live in today, huh? All right, but let's get back on track here. That we need to find actual values for that function of g. Of course, what that means is for us is that we need to understand what they're looking for if we plug in 2 into g and what that looks like. Okay. Yes, Claire has now welcomed me to the internet. I feel so welcome that yes, I have to do TikTok dances in order to receive likes on my own stream. What a way to go, as I'm trying to focus up here, trying to get the best score possible on this old exam. All right. So, if we were to actually plug in 2 into the actual function of g here, then we end up with actually putting in 2 where the limit of integration is for that function. which then of course just means we need to find is an area under the curve. And that also matches for g of -2 as well. This time going from 1 to -2. But of course, we're going to have a big what is happening moment, because when you read the integral, going from 1 to -2 doesn't make much sense. So we then need to then run it as a negative to flip that integral to make sure that we actually read it from low to high, from -1 to +1 for that same exact function. Some very simple limit manipulation for ourselves. Ah, yes, now Claire is saying that I need to blow a kiss to my viewers, which thankfully Nicholas got me covered on that one. So, Claire, I would expect that like to come in through the stream as well because of that. Again, I can always count on my boy Nicholas to come and clutch for something like that. Okay, so along with that, looks like we need to go and put ourselves through the operation of finding areas underneath these curves here, especially for the first function going from the limit of 1 to 2, which thankfully is just going to be this section right here, which is going to be a triangle. Again, 1 to 2 would be right there. Okay, for that type of graph. Now, something to note, of course, is that we have the point 1, 0 and 3, -1 as shown as the endpoints to that line. Okay, and so Nicholas wants a like goal. How much for that dance? Yeah, why don't you get 100 then, and we'll start. We'll get into negotiation once we hit that mark. I wonder if Nicholas will actually get there that fast. Okay, Claire is now offering to be my media manager for this. Yes. Well, if you have that time in your hands, we can definitely open that up to see if we can start getting clips off of my live stream so that we can actually garner some more interest for this kind of thing. Because I know for a lot of people online, this exam is just coming up in about a month and a week. So there's going to be a big scramble for people to actually get to this kind of stuff soon enough. Okay. So because, once more, that we have this line segment going from 1 to 1, 0 to 3, -1, it looks like we're going to need for ourselves to figure out what the actual slope is going to be for that little section right there to find the area underneath that curve. Okay. Let's see. Claire says that if I bought a plant clip to put on your head, would you wear it? Okay. A plant clip. We'll have to see. I think that will be a nice touch up to what I normally wear in terms of my usual content. But I think that will be a nice thing to get started with. But given your location, you might have to send that one over to me, and we need to wait for that to arrive first. Okay, so because of this, let's go ahead and find the quick slope for that line. So that means we need to go -1 minus a 0 over a 3 minus 1. To get that slope, which is going to be a nice -1 over 2. Again, that's the slope for the line going from 1 to 3 on the x values. Oop, that wasn't supposed to happen. Okay, and with that, we have everything that we need to then figure this out, because by having a slope of -1/2, again, that means we only really go down a height of -1/2. So again, the area for going from 1 to 2 f of t dt is going to be the triangle function of 1/2 and multiply now a base of 1 multiplied by a height of -1/2. And so this is the base, this is the height, given that this is going to be a triangle of the area underneath going from 1 to 2 on that graph. So with that, we just end up with -1 over 4 as g of +2. Okay, so that's the first set of the solutions for us. And then we need to go now from -2 all the way to +1, which begins back there. So this is the -2 mark. Okay, which that point up there is going to be -2, 3 as shown on the function. Then we need to include this whole section of the triangle, including with the actual semicircle ending at 1 there. So we have a lot to add here, right? So if we want to show that in terms of what we need to do here, so -2 to +1 of f of t dt. That integral is going to be the area. We keep that negative coefficient there of that triangle. And then, given the fact that this is a semicircle that's underneath the axis, we need to keep track of a negative area. So I think here we use a negative on the semicircle. Usually it's a good idea to keep track on our work here for all the geometries that we need to put together for us to then reach an actual result for this type of answer. Okay, so with the triangle, we then have a height of positive 3 on this. So we have a 3 multiplied by a 1/2, given that it is a triangle, and a base of 1. So again, that's the height, 1 is the base. So by going across that, that is a negative on the outside, that's a positive area of 3/2 for the triangle. And then for the semicircle, given that it is underneath the curve, okay, the semicircle here, as you can see from the center, will then get up there and have a radius of 1. Okay, so semicircle with a radius of 1 means that the area then, given the area of a full circle is pi r squared, again that's for a full circle. Instead, if we want to do a semicircle, that means we just take 1/2 of it. Very simple, right, for a semicircle for ourselves. So that just means with a radius of 1 there, that just means that we subtract it by 1/2 times pi on the other side. Okay, so with that, we can then easily do a little bit of distributive property with that negative coefficient waiting for us at the end of that checkout line. So the actual integral going from -2 to +1 f of t dt will then give us an actual positive pi over 2 subtracted by a 3/2 as a result. Okay, so I think just to keep everything together here, when we go to corrections, is that we have ourselves those 2 points after finding some nice areas underneath the curve for ourselves. Okay, and along with that, that should be enough for part A, as we took all the steps needed to find the areas underneath each of the curves that they're asking for that function of g. Okay, so let's go to part B. It says here that for each of g prime of -3 and g double prime of the -3, find the value or state that it does not exist. Okay, so in that case, we need to find the method at least where if g prime of -3 and g double prime of -3 will not exist in our case. Okay, so in that case, if we want to understand what g prime of x is in the first place in the generic sense of what that function looks like, that just means we need to go and take all of what g was already defined as, the integral from 1 to x f of t dt. And if we took the derivative in terms of x for that type of function, well, that just means with a clear understanding of the fundamental theorem of calculus, that means we just get f of x as a response to that derivative. Okay, and with that, again, already showing that because the variable is going to be replaced for where that limit was, that's going to be the result of the first derivative, while if we just go one more step and take a second derivative of g, that is the first derivative of t. Okay, so we need to find the value of each of them. So in that case, if we want to find g prime of -3, that means it's asking for f of -3, while the g second prime of -3 is asking for the first derivative of f of -3. Okay, both of which actually do exist, as you might be able to see here, given that back on the graph of f, the -3 on the x is shown back there, which is a nice point already on that graph there. Okay, and at least for us, it should be the point, because if that's -2 comma 3 and we end at -4 comma 1, we just need to subtract 1 off of the y's, going from 3, 2, and 1 there. So -3 comma +2 is the actual point that is on the graph for us right there. Okay, so because of that, we have just about everything we need here to then start solving these problems. First off, of course, is that the f of -3 already is defined on the graph as a +2, which is already the g prime of -3. So that is our first solution set already. And if we go with the first derivative, Again, the first derivative of the graph of f just means the slope along that line, especially at the point of -3. And as you can see, this is a positive slope increasing on the y values by 1 on each step of that segment. So because of that, f prime of 3 is just going to be a nice and easy positive 1, which is what they're asking for at the second derivative of -3. Okay. Very good. So looks like we have everything that we need on our side here to simply have all of the parts answered for g prime of -3 and g second derivative of -3 as another understanding of the fundamental theorem of calculus on that point. Very good. So again, looks like we have a lot of people coming in right now. So just as a quick reminder is that we are going over the 2012 AP Calculus AB free response question exam packet, which again has a total of 6 problems. We are going through question number 3 already, and any other math related questions that are sent through the chat will be answered as soon as possible, as this is just simply something we do off to the side if anyone else has any direct help that they need. Alright, so going on to part C here, we have ourselves that we need to find the x-coordinate of each point at which the graph of G has a horizontal tangent line. Okay, so then it says for each point, define if it is a relative, minimum, maximum, or neither. Alright, so we have our work cut out for us here, that we are looking for points at which the graph of G has a horizontal tangent line. That is a great vocabulary word for a lot of calculus students, given that if that's what they're looking for, they were looking to see that the first derivative of G at any given point is going to be equal to 0. Okay, so because of that, that just means that we need to refer back to our original definition of g prime of x from our previous problem as the actual function of f of x, which was already nicely graphed out for us at the start of the problem. Okay, so because of that, we can very easily go and refer back to the graph to see all the x values in which this is going to be true. So let's go take some notes here that for now, at the point of x is equal to -1, which was right there at the right crossing of the axis, that's going to be 1. And then another one, 1, 0, that's going to be the second point at which the function of f goes to 0 on the y value. Okay, so because of that, if we have the 2 points -1 and +1 as candidates for either of these. Okay, and so we need to define it if it's going to be a relative min, max, or neither. Of course, that means that we have to do our good friend, the number line analysis, in order to determine that. Of course, being that, we need to determine if the sign before and after those points, so at -1 and +1 on the x values, again, if that first derivative is below the x-axis or above the x-axis, that'll help determine what the look of the curve will be like in terms of being a maximum or minimum for ourselves. Right? So again, given that these -1 and +1 was already at 0, we need to look at the change of values right afterwards to see what that sign looks like for ourselves, if we can determine if they are minimums or maximums for our case. Okay. So going already back to the graph, we can definitely see a change here that going before -1, so all the negative answers after or before -1, those will all be positive values for us. And then after crossing that -1, we go to negative values, especially at 0, -1, as you can see on the graph. Right? So because of that, all the values before -1 are going to be positive values, and then all the answers after -1 is going to be negative values. But then something very interesting happens in the sense that at +1, we do hit the 0, but once you get past it, from negative numbers getting to 0, then afterwards we go back down to negative again. Okay, so with that, there is some very simple analysis that we can do here, because if we cross from positive to negative, so again an increase, the idea being here that because we are analyzing the first derivative of g, that's an increase followed by a decrease, right? So we're going up on the graph and then going back down on the graph. Again, that would mean that we are dealing with a maximum mathematically. While on the other hand, but if we go to a decrease, right? So as you see, we have a decrease on before positive 1, but after hitting positive 1, we have a decrease again, right? So if we decrease and then decrease some more, right, we actually have neither a minimum or maximum, because we are just going further down into negative numbers there. Okay, so because of that, we have all of the work there to prove that g of negative 1 is a local maximum, okay, and g of negative 1 is neither a minimum or maximum. Okay. It's a very simple number line analysis that calculus students should be able to do. Okay. So Nicholas then asks a question that what makes a min or maximum relative? Are there other kinds of mins and maxes? Yes, actually. This is a very interesting topic of discussion, because they do ask for absolute mins and maxes. So we say relative because, at least for that moment, mathematically, it's going to be a maximum in the sense that we are increasing into decreasing, right? Although this is a relative maximum, that does not guarantee it being the highest point on a function. A very quick example here, if we're just going to go off on a quick tangent for a moment here on this paper, right, is that if we have a nice looking function like this, and then it kind of curls upwards and it keeps going upwards like this, okay, and it keeps curling downwards like that, we have here, as you can see, that's a relative maximum, because we have a point where it increases going into a decrease. But as you can see, of course, is that even though this is a relative maximum, it is not the highest point of the function in the slightest. Same thing happens here, is that even on this point here, as we go from a decrease into an increase, mathematically that is a relative minimum, as a way to show that it is the lowest point of its area. But that does not mean that it's the lowest point on the entire graph, because the graph continues to decrease after that. Okay, right? So hopefully that should be a little bit of a difference, right? Is that we can tell for the area itself as a change of the slope going from positives to negatives, that would mean that it's a relative one, right? It could be the highest one of the entire graph. That will take additional math to decide. And also that is a question which might be asked at a later point on this exam, of you actually finding the truest, highest, or lowest point of the function. But at least for us, we use the term relative because we have not proved it being an absolute minimum or maximum. So those are the types that are usually prevalent in discussions of calculus. So hopefully that clears things up for Nicholas there. But at least for us, that does clear up for, on our end, the question C for us, showing that g of negative 1 is a local maximum, while g of, that's be positive 1, is neither, because we went from a decrease into another decrease, mathematically showing nothing. Yes, Nicholas says thank you, and that is perfect for us to move forward. Okay, so we can box this up as our answer here, and we can get over to part D. Okay, so part D says here that we have an interval here going for -4 to x to +3. It says here to find all values of x for which the graph of g has a point of inflection. That is a great word right there. Point of inflection, and we can explain why. Okay, a point of inflection. Now that is a great little vocabulary word once more for our calculus viewers, because that means that we have to go and take the second derivative of, not f, what am I doing? It's the second derivative of g, because that's what the function that's in question right there. And that means it's going to be equal to 0. That is the direct definition of a point of inflection. Okay, but going back to our previous definitions for all the work that we've done so far, we know that the second derivative of g is going to be the first derivative of f. So in our case, that point for us is the first derivative of f going to be equal to 0, which now this for us is going to mean that we need to find the points at which we have a min or max for the first derivative, right? Because that's going to be a change in the actual signs for that first derivative. Okay, so with that, we should have what we need to put that all together for us. Okay, so I think with that, let me just make sure we are on the right page for this. That in terms of all that we have in the graph at the start there, again, this is the graph of f, and we need the first derivative of f being equal to 0. That would mean that we are going to need the actual changes, again, positive, negative, being equal to 0 at each of those points that we see for this type of function. Okay? So for what we have here is that, what we might notice here is that, let me double check here. So we have a few candidates here of the changes. Again, that's at x equals -2 because we're going into an increase into a decrease at the -2 point. And then at 0, we have the same thing there. We are decreasing before we hit 0 on the x, and then increasing afterwards. Okay, and same thing actually happens for point 1 as well, because we're increasing up to 1, and then we decrease afterwards, right? So some candidates that we might be looking at is that if x is equal to -2, 0, and +1, we should try to see that, again, we need to follow an increase into a decrease, right? Again, a change in the slopes for the sign of each of them. Okay, so with that, we can run a nice number line analysis for the function of f prime of x for ourselves. So at -2, 0, and +1 on that. Okay, and again, we can take a look here. So at -2, we're increasing all the way up until we reach -2 itself on that graph up at the top. So that's going to be all increases leading up to -2. Then following -2, getting closer to 0, we are all the way decreasing, going downwards on that graph of f, meaning that the first derivative of f must be a negative value. So going from an increase to a decrease on that first derivative graph, that does prove that the x is equal to -2 is an inflection point. Okay, meaning that the second derivative was going to be equal to 0. Okay, then at the point of 0, again, we are decreasing and then getting back up to an increase after that fact. Okay, so by decreasing before 0 and increasing after 0, we are also showing that x is equal to 0 is going to be another valid result for a point of inflection. And then very lastly, as we're increasing, we hit 1, we stop, and then we go to a decrease again, going downwards onto the graph, meaning that the first derivative is then going to be negative there as well. So that's another swap in signs, going from an increase to a decrease for that guy, making it a a positive one, the negative in terms of the slope, but positive one is going to all be possible inflection points, because that means that the second derivative of g is going to be equal to 0 at that point. Okay, so that is just about all that we need right now for question number 3. We've answered from parts A to D with a lot of understanding how to find areas underneath the graphs and doing number line analyses across the board for these types of problems. Okay, let's go over to question number 4, and we will be able to then correct our work once we finish that problem. So let's see what we can do here. Okay, so with question number 4, it says here that the function f is defined by f of x being equal to the square root of 25 minus x squared for the interval of -5 to x to +5. Okay, and that is all the context that they're going to give us. Wow, that's very simple. So let's go ahead and begin with the first part of part A, telling us to find f prime of x in the generic sense. Okay, very easy for ourselves. So let's go run a nice differentiation here, f prime of x. But then that means we have a square root function to deal with. Ah, yes. only my first video series was about something close to that, where we can instead of calling it the square root for the sake of differentiation, we can call it instead the square root of 1/2 as the definition of a square root. And so that way we can go ahead and use with our nice derivative here in terms of x, we were going to use power rule to then decide where this is going to go. Right? So we bring out down that 1/2 from the exponent spot, and then we get the new derivative as the new exponent as negative 1/2 by removing 1 from that exponent spot. And if my camera can decide to focus back up again, my hand is literally right here, man. What is happening? Like, do we need? Of course, it's gonna do this right when we're about to get to the next step as well. All right, come on now. Yeah, you can see my lovely handwriting right there. And you decide to go blurry once it steps a moment away here. Come on now. Whatever. All right. Well, if I need to write while it's tilted up, I just might have to. Okay. Until it decides to really man, come on. Okay. Wow, just a little shift in light, and that's all that really needs. Okay. Good. Then hopefully this should be still good enough for us to move on through. So with that, we're actually not done with this part though, because we have to take the derivative of the inside thanks to chain rule as a result of that. Okay, so meaning that we need to then end up with a coefficient of negative 2x as the derivative of the negative x squared comes out from there. So we can then clean this up into a nice first derivative of the 2's canceling with the 1/2. So it's a negative, because that negative is still left out there as a result of the negative x squared being derived. And let's make sure we swap that up. I think I need to work on the way that playlist plays right now. But that should be good for that part. And so we then have a negative x on the numerator, and then with the negative 1/2 exponent, that's going to run everything else in the denominator as a square root of 25 minus x squared. Okay, a little bit inefficient in terms of stream-wise, but that is going to be the first derivative for the function of f. Okay. Then going over to part B here, it tells us to write an expression for the line tangent to the graph f at x is equal to 3. Okay, so a very nice and easy question here. Again, line tangent means that we need to go write the equation in the form. The AP test actually likes it in point slope form, which is going to be the slope of the function of x minus h plus k on the outside, where again h comma k is the point that it's going to be tangent to the function. Okay, so if we have the x is equal to 3 as the x value, we need to know the full coordinates of both being tangent to the graph of f, meaning that we need to first find that. So f of 3 by plugging 3 to the x values, that means we have 25 minus 3 squared. Okay, so as a result of that, we're going to go and take the square root of 25 minus 9, which means square root of 16, which for us is a lovely 4. Okay, so that means we did find the point of tangency for us. It's 3 comma 4 as a result of that. And so now we have the h and k, we just need to find the actual m slope, right? So slope at any given point, which is going to be the point at x equals 3, means that we need to find f prime of 3 as well, right? And given that we literally just found the first derivative as the first part of this question series here, we can then plug in those positive 3's into the equation itself. So divide minus 3 squared on the denominator, making it negative 3 on top, square root of 25 minus 9. So 3 over the square root of 16 is going to be negative 3 over 4 Again, this was going to be the slope at x is equal to 3 that we just found. Okay, that makes our lives a little bit easier because then we can plug everything we have in terms of the point and the slope that is needed to find that tangent line equation. So from there we get y is equal to negative 3 over 4 as the slope, multiplied by x minus a positive 3 plus 4 as the value of y waiting there on the outside. Okay, and that will do it for the tangent line equation. A very straightforward problem for us, which is quite nice. Okay, getting on to part C here, it tells us that let g be the function defined by g of x being equal to all of, and a piecewise function, f of x for negative 5 being all the way to negative 3 for x, and x plus 7 for everything beyond negative 3 all the way up to positive 5. Okay, so with that, they're going to ask if is g continuous at x is equal to negative 3. Okay, so looks like we have a little bit of work cut out for us, because for this is kind of an early point for many calculus students in their time in this class. But continuity is going to be defined in a few ways. For one is that we need to know that g of 3 exists. That's one part, right? So if you want to write in steps, the second step for continuity is that we need to take the limit as x approaches that number 3, okay, right, of g of x, again, must equal, this must exist as well. And then at least part 3, we must then prove that g of 3, the point, is equal to the limit as x approaches 3 from both sides of that function as well. All three of these must be correct, right? So as I note here, all must be correct to be continuous. I remember during my time, a lot of students would just say, oh yeah, it looks continuous to me, but that's not really good enough, especially on this exam. Again, we have to prove mathematically that this function is going to be continuous at that point. Okay, so let's take this one step at a time. G of 3, so plugging it in g of 3. So at positive 3 means that we're going to, why am I saying positive? It's negative 3, my goodness. I had a little bit of a moment there. It's negative 3 for the point that we are proving right now. So g of negative 3, in terms of the rules that we have defined earlier, right, the one that includes negative 3 is going to be the top function. Okay, so at g of negative 3, that means we are looking at f of negative 3. So then from there we have to plug it into our original f function that they gave us at the start of the problem, which is the square root of 25 minus 3 squared, which we've done many times before, which is going to be a square root of 16, making it a positive 4. Okay, again, this is going to be the negative 3, all of that squared, which makes it back to a positive 9 there. Okay, so with that being the response, looks like step 1 has been completed by us. Then we need to take the limit as g approaches x. This is the both sides. Okay, both sides of that limit. So let's see here. So does the limit as x approaches 3 from the left side of the function of g of x, does it match the limit as you approach it from the right side of negative 3? Okay, so both sides at negative 3 means that we have to go look at both the f of x side and the x plus 7 side, right? Okay, so at the left side, the lower side, which is going to be the top rule for us on that piecewise function, looks like that does match at, so we have we've already solved that earlier, there's a positive 4, and will that be equal to the one on the right side of the function at negative 3, which means that we have to take a negative 3 plus a 7 following the bottom rule of this piecewise function, meaning that we get 4 on both sides as we approach it from either rule, the top or bottom rule, getting to negative 3. So looks like part 2 is correct as well. Okay, and does it look like g of negative 3, the actual point and the limit from both sides, is that going to be the case? And at least for us, with the g of negative 3 being equal to 4 and the limit of both sides as x approaches negative 3 for g of x, that's also equal to 4. it looks like all of them are going to be correct. So we're going to say yes, g of -3 is continuous. The wording's a little bit wrong. It's supposed to be g of x. So g of x is continuous at x is equal to -3. We can box that up as the correct phrasing mathematically for us after all of our work proves it as such. Okay. Let's get lastly on to part D here to round things off for problem number 4. Now it says here to find the value of the integral from going to 0 to 5 of x multiplied by the square root of 25 minus x squared dx. Okay, looks like we got ourselves a work cut out for us because this is a non-calculator section for this part of the exam. So we got a few things going out for us. One is that we can easily solve this integration by hand because we have the two sets right there, 25 minus x squared on the inside of the square root with an x waiting for us outside. So we can't really split that up into two different parts. But something to note is that if we followed chain rule, that 25 minus x squared, if we took the derivative of that of the inside of the square root, that will give us the negative 2x as a response to that. And so if that were the case, we just need to deal with a -2 coefficient coming out of that integration. Okay. Now for ourselves, we can run this a few ways. I think I like to go dabble a little bit in u substitution as an easier way of understanding this type of problem. Again, being the fact that if we called u equal to the 25 minus x squared, that would mean the derivative of u in terms of that is going to be -2x dx like we've done before. If we're going to do substitution, we would have to then show for each of these what that will look like in terms of u instead. So we need to match everything one for one. We have the x dx, it's just that that -2 on the outside does not match. So by just putting the -2 underneath the du, we do have everything to match to then replace x dx with the u du over -2, while the 25 minus x squared will be replaced by du. Okay. Something to know, of course, is that we do not do limits until we actually substitute back into x. I think, at least for me, that's an easy way of doing things. So we can run this now indefinite integral for now of calling this the square root of u multiplied by du divided by -2. Okay. Now given that this is just a nice coefficient waiting for us, we can have that -2 wait on the outside as we take the square root of u du as an integral, meaning that we can run this integral as u now raised to the 3/2 power as a response to the exponent rule of integration, and we need to multiply by 2/3 coefficient waiting for us on that side. Okay, then we still need to evaluate the limits of a to b after we substitute back. That's the reminder for us there. So we can leave a negative coefficient of -4/3 on the outside as we then substitute back for u into going back into terms of x for ourselves, meaning that we have 25 minus x squared, all of this raised to the 3/2 power, evaluated from 0 to 5, as those were the limits of x for us to begin with. Okay, so with that, we have everything we need, looks like, to run this type of integration. So let's evaluate those limits. We can leave the -4/3 again as a coefficient. Let's plug in 5 first as the first limit of integration. So 25 minus 5 squared raised to the 3/2 power, subtracted by the 25 minus 0 squared raised to the 3/2 power, as it's going to be the top limit subtracted by the bottom limit from this integration. All right, 25 minus 5 squared, well, thankfully that all goes directly into a nice 0 for us, as 25 minus 25 is going to be 0. We keep that negative right there. 25 minus 0 squared is going to be 25 raised to the 3/2 power. So with that, the -4/3 weighting with a negative 25 to the 3/2, we can do the square first, the square root first, with the over 2 on the fraction, making it into a 5 to the 3rd power remaining for us on that side, which will then give us a -125 waiting on that end. the negatives will cancel from this multiplication. So this ends up as a positive 500 over 3 as a result of that integration. Okay. I think that works out pretty well for us. And so we have, looks like all parts going from A through D for part number 4. And that is enough for us to start correcting what we have answered so far, with starting from question number 3. Okay, so let's have a look at some of those answers and we can get back to some scoring. Okay, so back to what we had on that graph for question number 3. They were asking for the values of g of positive 2 and g of negative 2. And we gave them exactly what they wanted, with g of positive 2 being negative 1/4 by running the actual areas underneath the curve. And then we end up with pi over 2 minus 3 over 2 as a result of that area of the triangle subtracted by that semicircle. So both of those are good. So that's going to be 2 out of 2 correct for part A for us. Going over to part B, we then have the two parts of g prime of negative 3 and g double prime of negative 3, giving us a positive 2 as a result of understanding fundamental theorem of calculus, and then g double prime of negative 3 being positive 1 as a result of that second derivative, both of which would give us 2 out of 2 correct, to show how we can use fundamental theorem of taking a derivative of an integral to then simply solve for those values. Okay, going over to part C, we then have ourselves the horizontal tangent line parts here. Okay, so we have it at -1 and +1. Okay, and so because of that, we're looking to see that g prime of x being equal to 0. That's the way that we can find those relatives, mins, and maxes for the graph of g. Then by running those considerations, we understand that g of -1 is a local maximum, which is correct. And then g of +1, and given that it goes from decreasing to decreasing again after passing through point of 1, it's going to be neither in that case. Okay? So all three things that they were considering to give us points on, we have received all 3 points. So it's be 3 out of 3 correct for that part. Okay. Well, okay, a little plant bud clip is what Claire is referring to. Yes, we'll see. I don't know if you're looking to see if I can put clips in my hair. My hair is simply not long enough to put clips on it, but again, you can send anything over if you want, and we can try to see if that's going to be a possibility for us. I guess to spice up my looks more than it already is. Lastly, for part D, if you're looking for the point of inflection, again, that's the second derivative of g looking to be equal to 0. So all those points of -2, 0, and 1 were all indeed correct answers. Again, we need to show that the second derivative of g, or the first derivative of f, needs to be equal to 0, with our analysis showing that that was the case. So both of those will give us reasons to get 2 out of 2 correct on that part. And would you look at that, we have 9 out of 9 correct for this part as well. That is pretty nice. That's question number 3. So we got halfway through already, and we are perfect on our responses so far. I say that's pretty good. Okay. Then next up, we have question number 4 here, where we have to take that original function of f. Taking that first derivative gives us the negative x over the square root of 25 minus x squared. So that is the correct response to that. Understanding that we use chain rule properly will give us 2 out of 2 correct for part A. Okay. Then going to part B here, then we have you have to take the f prime of positive 3 there. Okay, and so yeah, we do end up with the exact answer that we were looking for of the equation of the 4 and the 3/4. Yep, just like that. Okay, and taking it is to understanding to take that derivative at positive 3 will then give us 2 out of 2 correct for that part as well. Okay, again, understand that they're looking for in point slope form was indeed going to be the right way of putting that together. And then next at part C here, then yes, we do need to show that we do the one-side limits. So we take the limits on either side of 3 so that we compare both the top and bottom rule for this definition of g. And so by doing that, again, we did match it as 4 being equal to either side of those limits, which is good, and which therefore, by matching it with the point of g of 3, g of negative 3 that is, by putting it all together, as they were both the point and the limit from both sides being equal to 4, that does give our answer that the function was continuous at negative 3. So that will be 2 out of 2 correct for us on that point as well. Okay. Lastly, at part D here, we can run the substitution as the way that they wanted, with setting up the integral now in a much simpler fashion of negative. Okay, that's hilarious. That is one mistake, unfortunately, already for us, because that wasn't supposed to be a negative 2 on the outside. That's a negative 1/2 on the outside. That is a very unfortunate mistake made on my end. And because of that, this should have actually been, instead of let me double check. So instead of running that 1/2 through, that shouldn't be negative 4/3. That should be a negative 1/3. Effectively quartering our response from a negative 1/3 multiplied on the outside, making it, instead of 500 over 3, a 125 over 3. Okay, so that is a little bit unfortunate the way that that had to go, but in any case though, the setup actually for the substitution was 100% correct on that end of being able to run the integral. And so other than that coefficient, that will give us 2 out of 3 correct for getting the incorrect answer for that part. Okay, so that will give us 8 out of 9 for part 4. Very sad that eventually there was a slip up on that end. But in any case though, we're still very well on track to breaking, I think, the highest score that we have. Hopefully by just missing 1, that would be the highest score that we have yet to achieve on the history of this channel. Okay, good. So we have ourselves only 2 more problems to go for questions 5 and 6 on this exam. And so with that, we have our last few things to go over, and then we can go check our totals for this packet. Okay. So we have a very interesting problem number 5 here, looks like. So let's go and copy that one down, and we'll see what we end up with here. Okay. So problem number 5 here, it says that the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Okay, so then it says here that at the time is equal to 0 when the baby is first weighed, its weight is 20 grams. Okay, then if B of t is the weight of the bird, in grams, at time t days after it's first weighed, it is first weighed, then we have this differential equation, d of capital B over d of t is equal to 1 over 5 multiplied by 100 minus capital B. Okay. So with that, it says here that let y be equal to B of t be the solution to the differential equation with initial condition B of 0 being equal to 20. Okay, very good. So at part A over here, after all of that great context, it's asking us, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams. Okay, so very interesting that we have all that together. Okay, so just to make sure we're on the same page in all this, we have a differential equation, d of b over d of t. That's the rate of the weight that it is gaining. Okay, and its starting weight is at 20 grams, right? So b being the actual weight of the bird at any given time. Okay, and so with that, we need to go and start answering the question if it's gaining weight faster at 40 grams or 70 grams, meaning that we need to go take that differential equation and plug in for the weight of the bird at 40 versus if we took the same thing and compared it to weighing it at 70 grams. Okay, so both these are rates at which it is gaining the weight in grams for that bird. So grams per the time just in years, or does it matter? As in days. Okay. All right. So with that, we can then plug in for each of them. So 1/5 100 minus 40, and then the other side is 100 minus 70. Okay. So it shows here that we end up with 1/5 multiplied by a positive 60, and then 1/5 minus 1/5 multiplied by positive 30. End up with 12, that's me grams per day versus the 6 grams per day as a result of those two values there. Okay, so with the obviously the larger one, the bird is gaining, right? So the bird is gaining weight faster at 40 grams than 70 grams. Right, we have all the work to show for it, and that should be part A already. Okay. Very good. So with that, we can then move on to part B here. It says here that we need to find then the second derivative, so the second derivative of dB over dt in terms of B. Okay. So, and then actually, so we have a graph here, so we can actually, I might have to transition over, because they actually specifically just for part B on this problem, they want to make an explanation as to why that shows. But I think I should have the space. No, you know, I got a space to copy it over once we're done. Okay, but let's first start this with this first part of problem B. We want to find that second derivative of B, dB over dt. So by doing that, we can go and set it up that it's going to be that 1 over 5, 100 minus b, all of this taken into a second derivative. Okay, it should be d over dt, that is. Okay, so because of that, I think first we need to go and distribute that 1/5 across the board to make sure we are following each step of our differentiation, meaning that we have a 20 subtracted by b over 5, taking that as d over dt, another derivative. So given that we can distribute that differentiation across that parentheses, we just end up with a 0 from the 20 subtracted by now the first derivative of b divided by 5 as the coefficient rule kicks in. And something to note, of course, is that we're doing the implicit differentiation as a result of that, given that the derivative of b is not going to go to 1 because we have a derivative of b already earlier. So that makes it a negative 1/5 coefficient waiting for us as we then plug dB over dt back again from the start of the problem. It gives it a positive 1/5 multiplied by a 100 minus b again. Okay, so by doing that, we can solve this very easily algebraically over a negative 1 over 25 as a full coefficient, 100 minus b, giving us a negative 4 plus b over 25. Okay, and to make this look a bit nicer is that we can then finalize our answer as going to be b over 25 minus a whole 4. That is going to be the second derivative of that graph. Okay. And so what that looks like in terms of what we have here, right? Again, we have that graph, so I can copy that over really quickly here, just to make it all assured that we need to explain what is happening, because we start at 20 there, and then we end up at 100 eventually. So that's time in days, and that's going to be b in the weight. So the graph shows a little something like this. It flattens out about 100. Okay. So they want to show to us about what is happening in terms of that graph. Again, does this match exactly what we have with that second derivative? The answer, of course, is going to yeah, it says here that that b cannot resemble, right? So can't resemble what we have so far. Okay, and so the reason why it wouldn't be that way for this is, of course, because we need to be at least, right? So at the mark of 100 across the board, right? Again, so at t is equal to 100, that is going to be the second derivative will then be equal to 0 at the time being equal to 100, right? This is where the inflection point needs to happen, right? So we need to change the curvature to the concave down to concave up as we go past 100 days. Okay. The main issue, of course, being that this curve is a concave up to start, because we're curling upwards at the start of the graph, and then we later curl downwards after the fact, right? So that is the wrong curvature that will describe the second derivative of b that we just found here as a way that we started concave down. So again, being that if we have that 100 being the mark in which it is equal to 0, we need to go concave down first into concave up. That's given all the work that we've shown for the second derivative of that implicit differentiation. But because it's going in the reverse order of going concave up and then concave down as a result of this, that will clearly tell us that the derivative does not match, and that is this graph is not a correct representation of what is happening to the actual function itself. Okay, so we have that as a response for ourselves, so we can keep that before we go to the next part here, part C. It says here to use separation of variables to find the generic function y is equal to b of t. Okay, and then initial condition b of 0 is equal to 20, as they stated at the first part of the question, in order to help us with that. Okay, so going back, we have the first derivative db over dt. So if we want to go and separate it out to find the function of b once more, we need to then indeed separate everything into each category for us to do that. Okay, so what I'd like to do first is to run that distribution of the 20 minus b over 5 as a result of that. But because we need to have everything in terms of multiplication and division for that to be moved, in that case, then we can run things over as db over 20 minus b over 5, us to one side, and then dt being multiplied over to the other. This is how we can set it up to have our own integration on both sides as two separate functions on either side of the equation. So with that, we can run the integral of the natural log of 20 minus b over 5. Okay, and with that, we would then need to keep track of that negative 1/5 coming out as a coefficient. So we have a negative whole 5 waiting for us to cancel out with that negative 1/5 coefficient, being equal to t plus c on the other side. Okay, so with that, we can then go ahead and solve using the initial condition that we started with. So we have the negative 5 natural log of 20 minus 0 on that end is equal to, b is 20, sorry. So 20 over 5 is equal to 0 plus c, t being equal to 0 on the initial condition. Okay, so with negative 5 multiplied by the natural log of 20 minus 4 being equal to c, c in this case is negative 5, the natural log of 16. Okay, so with that we can then start separating everything out by plugging back in the c and then isolating for b. So that's equal to t minus 5 times the natural log of 16. Okay, then we can divide everything by negative 5 on both sides because we need to work our way to isolating b on one side of that equation. Okay, so that's going to be the natural log of negative 20 positive 20 minus b over 5, and then it will be negative t over 5 plus the natural log of 16. Okay, then we can shove everything under the exponential of e to get rid of that natural log, meaning that we have a positive 20 minus b over 5 being equal to e raised to the negative t over 5 plus the natural log of 16 all in there. We can split this across the addition in the exponent spot as simple definition of exponents there. So in this case we get the multiplication of e times natural log 16, which that will then cancel into a coefficient of 16, e of negative t over 5. Okay. Then lastly, we can subtract the 20 and then multiply by a negative 5 on either side, giving us the end result of the let's see, there's negative 80, I believe, negative 80 e raised to the negative t over 5, and the negative 20 multiplied by the negative 5 will be a positive 100. Okay, so it's a little bit of extra work to be done there, but that should be the proper way of putting all of that together on that side to ensure that we end up with everything that we need for ourselves. Okay, so I think that is going to be all that we need. Again, this was just simply a lot of additional algebra and math to work in, but the main purpose, of course, is that we did do the separation of variables right there as two integrations on either side of the equation, and then solving for that initial condition c in order to get an actual function of b of t at the end of all of our work. Okay, so that is question number 5. So we have one more to go, question number 6 with 4 parts, and that should about do it for the packet for today. Okay, so question number 6 here, it says that for 0 being going from t to 12, it says that a particle, we have that all in focus, a particle moves along the x-axis. Okay, the velocity of the particle at time of t is given by v of t being equal to the cosine of pi over 6 multiplied by t. Okay, the particle is at position x is equal to negative 2 at the time is equal to 0. Okay, so that's all the context that we need. So they're going to question A. It says that for the interval from going from 0 to t to 12, when is the particle moving to the left? Okay, so if we're looking to see if particles moving to the left, that's a great phrase right there for us to understand that. We're looking for the v of t being less than 0 during that time frame. Okay, so we need to know the entire interval of time in which this is going to be the case for the actual function. Okay, now it's getting just slightly blurry. Would you mind focusing up on that, please? So like just like here, and okay, there you go. Okay, so because of that, we need to go then see what we're looking at here. Okay. So yeah, going from there to 12. All right. So noting here that so something to note is that at t equals 12, again, that's going to be the cosine of pi over 6 times 12, which is going to be cosine of 2 pi, right? So looks like we're going across the entire interval of 2 pi across the entire cosine, meaning that, again, we have the entire section where we go from, again, if you remember the cosine function, basically it's going to be starting at 1, we go all the way down, and we go all the way back up, right? This is the generic cosine function. Okay, so we have all this section here that we are going underneath the axis, which is what they want in the first place, right, for us, which thankfully for ourselves, we can also take that note, right? So in cosine of, and going from, right, going all the negative sides for cosine is after it crosses the 0 at pi over 2, right, going all the way to 3 pi over 2, again, that's when it's less than 0. Right, some very good pre-calculus reminders for ourselves there, but I think that's plenty for us to work with that. Okay, so because of that, we need to know those two intervals for this entire part of that particle. Okay, so given that, we want to know pi over 6 times t at pi over 2, and all the way when it goes the same thing at 3 pi over 2 as the 2 points where it's going to be underneath the x-axis as a result of the cosine. Then we can replace it with t being equal to positive 3, and then t being equal to, if we multiply the 6 across and take care of the pi, that's going to be 3 times 3, which is 9. Yep. Okay, so just a little bit of an algebraic response here of what those values of t is going to be. Okay, if we were to show the work here, is that we had the pi over 2 on one side, multiplying by the reciprocal of 6 over pi, and those cancel, we end up with a positive 3, and the same thing happening with the 3 pi over 2 multiplied by a 6 over pi. Those pi's cancel, and then we have a 3 times 3 on the outside, making it a positive 9. Okay, so because of that, we then end up with the entirety of the cosine, not the cosine, but yeah, the time interval. So this is when t is going between 3 and 9. It will not include 3 and 9 because those are exactly when it's equal to 0, right? Is equal to 0 at that point. So that is going to be the interval for the times when the particle is moving to the left for that question. Okay, so part B says that we must write, but do not evaluate, an integral expression that gives the total distance traveled by the particle from time is equal to 0 all the way to time is equal to 6. Okay, so a very interesting note here that we need to keep track of for this is that we're looking for total distance that is traveled by the particle. Okay, that means we need to take the absolute value of velocity as an integral, right? That's what that means for total distance, because we are not going to subtract any of the negatives. We're actually going to add that to the total amount that has traveled. Again, noting that by taking the integral of velocity, again, that's how we get to distance. Okay, so if you want total distance, making all the negatives back into positives, we need to take the absolute value of that velocity function. So because of that, we need to go take that integral going from 0 to 6 of the absolute value of the v of t function, so absolute value of cosine of pi over 6 t dt. Okay, and this will be total distance. A very quick question, just testing us on our understanding of definitions, and that is exactly what is needed for us to move on from part B. Okay, and so then from there it says that we want to find the acceleration of the particle at the at the time of t, okay? So then they're asking, is the speed of the particle increasing, decreasing, or neither at the time is equal to 4. Okay? So because of that, we need to go ahead and see what we're looking at across the board for that. So let's go take this one at a time. We need acceleration of the particle at t. Of course, acceleration is just the definition of the velocity function with the derivative respect to time taken against it. Okay? So because they're asking us to just find the generic form of that, we need to just take the generic derivative of v of t. So with that, it's the derivative of cosine of pi over 6t. So we take the derivative with respect to time for that guy. And with that, we will then just need to go and follow a bit of chain rule first after taking the negative sign of pi over 6 times t, and we multiply it by pi over 6 as a. So that's negative pi over 6 multiplied by sine of pi over 6 times t, just like that. Okay, so that is going to be the acceleration function, a nice simple chain rule that we just had to deal with for this time. What is happening to, let me double check here, I think something, okay. Looks like we're running into a little bit of an issue. Okay. All right. There was just a little bit of an issue with what we had so far, but I think we can keep it up from there. I think we should be fine. Okay. Pretty sure other people let me know in the chat if there's any issues with the stream quality so far. Okay. But continuing forth, we still have to then describe what the speed of the particle is going to be at the time is of 4. Okay. Speed, of course, that is going to be the analysis between the acceleration and velocity, right? So again, if we have an increase in speed, that means both the velocity and acceleration need to be either greater than 0 together, or the acceleration and velocity need to both be less than 0, right? Speed does not care for the sign of velocity acceleration. They just care so much that they're going to be the same for that. Okay. Then in that case, the decrease, right, is that the velocity and acceleration are different signs on that. Okay. So because of that, I think we have everything that we need to then put this last things through here for ourselves to ensure that we are increasing or decreasing the speed. So at the velocity of 4, we can take a note of that. That's going to be the cosine of pi over 6 times 4 as the simple plug-in of that velocity function that we have so far, which is going to be the cosine of, by simplifying that, is 2 pi over 3. 2 pi over 3, of course, thanks to our lovely knowledge of the unit circle, because I'm sure no calculus student would ever forget that, is that because we're beyond the pi over 2 mark, that means we're going to be negative. We don't need to know the exact answer, of course, but of those who actually knew that, the actual answer would be just negative 1/2 as a result, thanks to the unit circle. And then we'd go take it for the acceleration as well. So that's going to be the negative pi over 6 multiplied by the sine of pi over 6 times 4. Okay, so with that now, we can run that acceleration equation, which is going to be the sine of 2 pi over 3. And once more, for those that actually did memorize the unit circle and kept up with all of their studies on that regard, that would be a sine resulting in rad 3 over 2. Okay, it's still going to be positive because we remain positive up until sine reaches the value of a whole pi, which gives us a negative rad 3 times pi all over a 12. Yeah. Okay, so it looks like both of them are going to be negative for the velocity and the acceleration, and our conclusion from there will show that the speed will be increasing at the time is equal to 4. Okay, Right, so we have all the work to show for both the acceleration function, that was the a of t shown at the start of the problem, as well as all the analysis needed to have an increase in the speed at the end of our work there. Okay, let's get to the final part of part D of question number 6, and let's see to what we finally scored here. Okay, so it says here to find the position of the particle at the time is equal to 4. Okay, very interesting, because we already have, again, as a note that they started earlier in the problem, that a position point is given, so x of 0 at time is equal to 0 is -2. Okay, so if you want to find a position at another time from this, it looks like we need to bring up our old friend fundamental theorem of calculus in order for us to find that exact point, given the fact that if we then took the integral of the velocity function, again, that would give us the original why am I blinking? But it's still the position function, that is, yeah, plus c if we did it indefinitely. But fundamental theorem will work out in another way, that if we then plugged in for actual limits to the definite integral, like for example 0 and 4, given that we know the time of 0 position and we want to find the time of 4 position, that will just mean that by running the integral itself, we will then take the difference between the position at 4 and the position at 0, one of which we do want to find as a result of our work there. Okay, so then if we did want to find it, we then just have to move the position of 0 over, and if we then ran the integral of the velocity of the cosine of pi over 6 multiplied by t, just like that, okay, then we should be able to find the position at 4 mathematically, all waiting there for us at the end of our line of work. Okay, so why don't we get right on with it? Let's start over here on the right side because we have a bit of space there. So at x is equal to 0, that means it's -2 at the position, adding it with, now if we integrate for the cosine of pi over 6t, that means we need to go back to a positive sign of pi over 6 times t, but accounting for the chain rule at the end of that, there's something, make the 6 a little bit bigger there. Okay, so accounting for the chain rule, we actually need to multiply then by coefficient of 6 over pi as a result of that. Okay, we then will need to evaluate it going from points 0 all the way to positive 4, and then we'll be able to see what we end up with because of that. So at -2 plus all of 6 over pi, then running the actual integration limits there, so it's going to be sine of the 4 pi over 6 subtracted by the sine of 0. Okay, then from there, right, we will then go and see what that looks like for us in terms of the final result of the integration there. So sine of 0 goes to a nice easy 0. 4 pi over 6 is another way of writing 2 pi over 3. And what we did earlier ourselves was just going to be rad 3 over 2 as the sine of 2 pi over 3. That, again, we should already know from the unit circle. So by leaving the -2 on the outside, that's going to be 6 over pi multiplied by rad 3 over 2. Okay, and so we can then cross cancel the 6 with the 3 there. So it's going to be a positive 3 times radical 3 over pi subtracted by 2. Okay, it's a little bit of a weird situation for us on that matter, but at least for us that has been isolated as the position at time of 4, mathematically showing what that's going to be like at a very specific time. Okay, so I think that is going to be all that we needed for problem part D there, as we showed all the work that we needed. So let's get to grading these last parts, and we shall find what our total will look like at the end of all this. Okay, so going back to part 5, the last one that we haven't corrected yet, we have ourselves at part A. Again, they're asking if the bird was gaining weight faster, if it was at 40 grams than 70 grams. Yeah, so by running either the dB over dt, that way they were looking for, at those exact values, we can then show that the bird is indeed gaining weight faster at the 40 grams rather than the 70 grams because of those rate equations that we had. Okay, so by using both the derivative and getting the right conclusion, that will be 2 out of 2 correct for us on part A. Okay, then moving forth on part B here, it is then going to ask us to find that second derivative. Okay, so by running that second derivative, I distributed the -1/25, but in any case though, that is going to be enough to show that we did indeed get the second derivative in terms of just B. Okay, and then they asked us if it can't resemble what we have, but yes, we did show that it needs to be concave down first and then concave up, while the graph that they showed us started concave up and later shifted concave down. That is simply not the curvature of the graph that was mathematically shown on that second derivative. And so because of that, that is enough for us to get 2 out of 2 correct on part B. Okay, then moving on to part C, our lovely separation of variables. We do need, this is actually worth a total of 5 points on part C. So let's see what we end up with because of that. Okay, so separation of variables was indeed correct to move everything over to one side. Okay, and then having the dt, they kept the 1/5 on one side, but in the end, by getting the right answer, it really doesn't matter on that sense. But by running the integral, we do end up with the negative natural log on one side, including the 100 minus b, and then the t plus c on the other end. Okay, keeping up with the constant of integration, we need to make sure that we actually run the solving of, let's see, where did that happen? Oh yes, yep, by actually solving for the initial point, again by plugging in the 0, 20 as what they described at the start of the problem. Okay, and so by that result, we end up with an actual answer to C. Okay, and because of that, we actually run this all the way to the end with our work of the -80 multiplied by e raised to the -t/5. Okay, and then adding that 100 at the end was exactly the way that they wanted you to show this. Okay, so because of that, everything is indeed correct work-wise and our final response. So that's going to be 5 out of 5 correct, as the separation of variables was indeed correct for this type of problem. Okay, as a note that I've made many times while correcting especially problems like this of separation of variables and solving for an initial condition, again, they will tell you on this type of correction packet that if you, so they tell you that if instead you have no plus c, the maximum you can get is 2 out of 5 points. Okay, that is a hardline rule that the test graders will always have, because running indefinite integrals means that you always end up with the plus c. We just need to solve for it at a later time. Okay, and then as well, another if is that if you did not separate variables, okay, you actually get a 0 out of 5. Okay, if that were the case again. So if you did not move all the b's over into the denominator of the db as you needed to do to actually run an integration, you would get 0 out of 5 points because of that. A very serious crime for many students that might not even do that. You really kind of fail out on problem number 5 entirely if you don't do that. Okay. Another note, of course, is that if I were the test graders, if my students forgot the plus c at the end of their indefinite integrals, I would be much inclined to give them 0 out of 5 as a result, because they simply don't know how to do indefinite integrals. But at least some of them will receive a little bit of mercy if everything else somehow managed to be correct, which I highly doubt it. But nonetheless though, our work still shows that we did everything that they want us to do. So because of that, part 5 did indeed receive the full points of 9 out of 9 as a result of all of that. Okay, so going back to our main packet, we can take that record down of getting 9 out of 9 on part 5. So looks like we are very well on track and receiving the highest points we have ever so far on our result of this type of problem. Okay, so let's go over to part 6, the very last problem on this packet, to see what this ends up with. And then from there, we'll try to see what our total value is going to be like. Okay, so we have for ourselves at part A that we end up with the velocity at, again, when we are moving to the left, Again, that meant that in the cosine function needed to be underneath the x-axis, as I had shown in that drawing there, which by running some very simple algebra with some pre-calculus knowledge there, that would just mean that we ended up at the time of 3 all the way to 9 was going to be the negative values for the cosine function of that velocity. So because of that, by showing that we were looking to be underneath 0 for that time, and the interval going from 3 to 9, as showing properly on the algebra there, we do indeed receive full points on part A. Okay. Then going on to part B, it tells us to write but do not integrate for the actual total distance. This was a very quick one because total distance just means that we have to take the absolute value of the velocity function. Again, a simple definition check was all that they're doing for us, so that was really just worth 1 point for us to do that. Very quick and easy for those who understood how to do total distance of velocity. Again, by taking its integral with an absolute value so that all the negative values get added into the total distance from there. Okay. Then from part C, we have the actual acceleration function given out by taking that first derivative. Okay. So a of t being negative pi over 6 times sine of pi over 6 times t. That was indeed going to be correct for the acceleration function. Then by plugging in for 4, again, we have to both check the velocity and acceleration at time is equal to 4, right? The negative root 3 times pi over 12, that was going to be indeed correct. And the velocity at negative 1/2. And because they were both negative values on the velocity and acceleration, right, the speed will be increasing at time is equal to 4. So because of that, we get all 3 points that were assigned to part C because of that. Okay. Then to finish everything off here, by us running the fundamental theorem of calculus by adding that x of 0 to the other side, as a result, again, a fundamental theorem of what we understand what definite integrals truly are. We were then able to put everything off to one side, then end up with a negative 2 plus a 3 rad 3 over pi, using that initial condition of x of 0 to be adding to the other side to then isolate x of 4. And that is the exact answer by running the actual definite integral. So from there, that is another 3 out of 3 correct on our side. Okay, so because of that, we do get a full 9 out of 9 correct for this part. Okay, which then means that we indeed have broken a channel record. Amazing. Hey, yeah, we've actually, other than one very small mistake that I made on question number 4, we have received 53 out of 54 total correct on this exam packet. I say that's pretty good, since we've actually, if you were to change this to a percentage really quickly here, let me see if I can swap the screens over for just a second here. And that, if indeed we get 53 over 54 correct across the board here, that ends up with a 98.15%. Very nice. It very well could have been 100 if we didn't make one simple mistake on that problem with carrying over a negative coefficient. But nonetheless, though, we had exactly what we needed to get a very high score, the highest yet on our whole channel history. So I think with that, that will indeed conclude what we had so far for this exam packet, because we are able to look through all that we have for this packet. Okay, so that will be it for today. I think this was fairly successful for all the things that I was able to explain. And again, that AP test is coming up within just another month or so. And so with that, we have just another stream coming up next Tuesday. So I hope to see many of you there during that time as we go over another packet. But with that, that should be about it for today. Again, all of the questions that were answered either through chat or again through the labcodemath@gmail.com email, we can turn your questions into answers. Should be an easy way for us to continue to garner a bit more support for what we're doing out here for people that are going to take this exam within the next month. All right, so because of that, I think that will be really about it for today. We'll be back again on Tuesday, and we hope to see you all soon.